Hi, this is Alex Epstein. Today I'm presenting my second physics lab, focused on the projectile motion of a falling object, specifically a wadded out paper ball. The analysis is guided by Newton's second law, and we're going to use this to iteratively predict the object's motion, relying on the velocity update formula and our position update formula for our glow strip code. In a real environment, we must consider more than just than gravity, so we model the drag force due to air resistance using the equation F drag equals BV squared, as shown in the diagram. So gravity acts downward and drag acts opposite, so we expect the vertical velocity to change throughout the flight. Okay. The experiment was conducted with a ball mass that was approximately 0.0028 kilograms, which is pretty much the size of paper. I recorded the motion at 60 FPS, so the time step was 0.017. And then by analyzing the first two positions in the tracker, the initial position at 0 and the first subsequent position, I got an initial velocity of negative 0.003 in the y direction. And this was used to initialize the glow strip code. Calculating the drag coefficient B analytically is really difficult because there's a lot of environmental factors. So we had to use a trial and error approach, and we found that B equaled around, here you'll see. There we go, around 0.005. So for the code, in the model, we had a while loop that simulated the motion. Inside this loop, we were doing calculating the weight force and then calculating the drag force based on the square of the velocity. Then there's some to find the net force, and then that's used to update the ball's velocity. So the blue dots, here you see. Now for our experimental data, the blue dots represent the experimental data and the lines show our models. So you can see how the trajectory is affected by the initial velocity and the angle, and with the gravity only, it starts to go down, but with the drag, it went a little farther. Yeah. So what does this mean? Basically, since gravity is only, it goes much closer, and the cause of error are air resistance, air with tracker. This is why it's a little bit messed up, even though the red one should be going farther. So if you extend them to find the terminal velocity, this occurs when the drag force equals the weight force, giving you a net force of 0. So looking at the velocity in the time graphs, my gravity only model predicts that velocity will increase forever. However, the drag model finds about a 4.34 meter per second, where the curve eventually levels off. For what if it was flown straight up, with the same initial speed, the time to reach the ground would be significantly longer. So the ball would first have to decelerate to 0 at its peak height before falling back down, which would add extra time. Yeah. And then if we find a scenario where F net isn't 0 in the horizontal, if a constant force were applied, the horizontal velocity would continue to increase, but the acceleration, since the acceleration is non-zero. So the final velocity would be greater than the initial velocity. Thank you for listening.